Okay, good morning, everyone. Hope you had a good weekend. Is everyone excited? You're nearly at the end of semester. Last week of new material. Can I get a cheer at least? That's a Monday morning cheer if I've ever heard one. Okay. So this week we're going to be talking about some applications of graphs. Last week we introduced graphs, and we just went through some principles of things like terminologies like what's a vertex, what's an edge, what's a path, what's a connected graph, and so on. We're going to be thinking about how we can apply these, first of all, to food webs this week, and then we're going to be revisiting some compartmental models that we actually looked at earlier this semester, and thinking about what they mean when they're in graph form. And then we're going to think about, on Friday, things called Markov chains and how we can use those to understand things like page ranking algorithms. Okay, so hopefully you guys have met food webs before. Who's met food webs before? Okay, great. So the actual context should be fairly familiar to you guys. So I won't dwell on what a food web is. What I will talk about a little bit, though, is that we're applying these ideas of directed graphs or digraphs that we discussed the other day. So a directed graph is basically just a graph that has some arrows on it. And in the context of a food web, those arrows are indicating what eats what. And so it indicates some flow of energy through that food web. So we can think about what happens with these food webs if we, in terms of their trophic levels or trophic status. And these quantitative measurements give us some indication of what, how important a species is in a food web, also its place in that food web as well, okay? So the pre-lecture went through various examples. We can calculate this by shortest path. So for example, for sea otters here, we calculate the trophic status as being the shortest distance between a primary producer, so that's something like a plant, in this case kelp, and that species. So there are two paths that we could take to sea otters. There's this one here on the right, which has length 3. And this one here on the left has length 2. We're taking the shortest path in this case, and so sea otters have trophic level 2. There are different definitions that we can have for these things. We could have the longest path, in which case the trophic level of sea otters would be 3. Okay. Each of these has a slightly different interpretation, which are discussed in the pre-lecture, so I won't again go over those again. Trophic status is a bit more complicated than the path length ones. Here, what we're doing is we're saying the trophic status of a species is equal to the sum of all species which have path length k times by that number of species that have path length k. Okay, so this one's a little bit, I think, the word definition of this one is a little bit complicated to understand, but actually working through it is a little bit easier. And we'll go through an example of that today. Essentially, if I take the example of, say, let's take sea otters here. First thing I do is I look at species that have path length 1 feeding into sea otters. So that's sea urchins and large crabs. So there are 2 species that have path length 1. Then I can look at species that have path length 2. So there's 1 species, small fishes here, that have path length 2. And then I look at, oh, sorry, there are 2. There should be, oh no, sorry, we're going by the longest path. I've completely forgotten what the definition of this was. We're going by the longest path. So there is 1 species that has the longest path length 2. And in the case of kelp, it does have path length 2 here, but we want the longest path. So it has 1 species of path length 3. We add those things up, and that gives us the trophic status of 7 for sea otters. The last one that was introduced in the pre-lecture was this idea of a weighted trophic level. This we're thinking about not only what a species eats, but what proportion of its diet is made up by those different things. So in this case, sea otters, we're saying 70% of their diet comes from sea urchins and 30% of their diet comes from large crabs. So in this case, it's slightly different to all the cases before. All the cases before we had, our primary producers had trophic level 0. But when we have a weighted food web, we say that the trophic level of our primary producers is going to be 1. And then for everything above that, we just do 1 plus all the things feeding into it, weighted by their proportion, weighted by the proportion of the diet of the species that's eating it. So again, I'll use sea otters as an example here. Sea otters, we have this 1 at the beginning, so we do 1 plus. Now 70% of its diet comes from sea urchins, so we have a 0.7 here, times by 2, which 2 is the trophic level of sea urchins. And then 30% of its diet, 0.3, times by the trophic level of large crabs, 3. We add these things together, okay? So these are just, this is essentially just a repeated process of calculating these different trophic levels, okay? One thing that wasn't covered in the pre-lecture but is important is we can think about what happens in these food webs if one of the species is removed. So we'll go through some examples of this, but we can think about, say, what happens if sea urchins were removed from this food web? Well, sea otters are going to lose 70% of their diet. We could think about what happens if small fishes are removed. Well, that means that large crabs are going to lose all of their diet, so they'll go extinct, and sea otters will lose 30% of their diet. Okay. I think some of this is best illustrated by going through some problems, but does anyone have any questions before we start problems? Okay. Okay, to start off with, here we've got a food web. We haven't identified what these species are, we've just given them letters here. I want you to go through and identify, first of all, the producers. These are primary producers, things like plants. Then your herbivores, predators, and top predators. Okay, once you've done that, I want you to think about this thing that I've just talked about here. What effect will we have if we remove species G? If species G goes extinct, what are the knock-on effects? Likewise, what are the things that will happen if species A becomes extinct? And then after that, find all the directed paths with initial point at 1 primary producer and terminal point J, so up here. Okay, have a go at that. Chat with your neighbors about how to do that. Okay, see how you guys got on? I'm afraid this is an audience participation one, so I'm going to need you guys to shout things out. Okay, so first of all, let's identify the producers. First producer. A. Nice. I was expecting a really pathetic. Okay. Next one. B. Next one. C. Isn't this a lot more fun? Yeah. Well, as fun as it can. Let's be realistic. Okay, herbivores. Okay, so herbivores, just to clarify, herbivores are going to be things that eat our primary producers, okay? Assuming that our primary producers are in fact plants here. So D, okay, another one. E. And again. I'm going to start framing all of my questions like this. This is way more fun. Okay, predator. H. Okay, H is a predator. I. Any more? So here, I realized in the pre-lecture, I distinguished between predators and top predators. What I should probably do is we should say that G, J, and K are predators, and then have the additional quality that they are top predators. So let's call them predators, and then I've just told you the answer anyway. But I'm sure you realize that G, J, and K are our top predators. I mean, it would be implied if it's a top predator, then it has to be a predator, but for completeness, if someone said what are the predators here, you should probably include G, J, and K. Okay, sorry, was that a question? So it would be an omnivore, but it is a predator. So really, we could also split this down further into this being an omnivore if we wanted to. Yeah, a good question. Any other questions? Okay, part B. So part B is where it becomes a little bit more tricky in terms of what we can and can't say. So part B says analyze the effect that species G becomes extinct. Okay. This kind of question trips a lot of students up when it comes to exams, because we need to really distinguish between what we can say will definitely happen and what might happen. Okay, we don't want to start imposing additional things and say this will happen, this will not happen, because when you start removing species from food webs or adding them into food webs, there are lots of complex ecological feedbacks that occur, and we don't know for certain what will happen. Okay, so what can we say for certain that will happen if species G is removed? Well, this arrow here is going to go, and so species D will lose a predator. So that's what we can say for absolute certain as to what that means, okay? Suppose this is a mountain lion and a rabbit. The rabbits no longer have mountain lions as a predator. So that's what will definitely happen, but there are lots of other things that we could say that might happen. So what might happen? Well, as species D has lost a predator, I'll put this as might happen. Things like species D might increase. The population size of species D might go up because it's lost a predator. What other things might happen? Well, as there's more species D around, maybe this is grass here. So species A and also species B, both of these things might go down because they're both eaten by species D. So those things might happen. We also might see, say, species H. If there's more rabbits around, this might be another predator, say coyote, species H might go up. But this is where these complicated feedbacks come in. If there are more rabbits around, maybe coyotes start switching and eating more rabbits. So maybe species D doesn't actually go up, right? Because if there are more rabbits around, the coyotes might just switch and start eating more rabbits, and there might be no net increase in rabbits, and so on. So this is when we're getting into our speculation that we don't really know. So this model here of a food web is just representing the relationships. It doesn't tell us anything about the population dynamics. The last few weeks when we've been doing our nonlinear and even our linear systems, we were talking about population dynamics. If you wanted to understand what was going on between all of these species in this food web, you'd maybe need to have lots of nested predator-prey models or competition models to understand what's going on. Here we can only speculate. Okay, so like I said, distinguish between these things that will happen and that might happen. Okay, likewise, part C, so analyze the effect that species A becomes extinct. Okay, so species A becomes extinct. What things can we say will happen? So species D will lose a food source. Things that might happen, we can say, well, maybe that means that species D will go down because it has lost a food source. Note there are two arrows coming out of this A. It's also coming to E. And E only has this one food source. So species E will go extinct. Now, there is always the possibility that maybe it will switch food source, but we don't know that. That would be speculation, okay? So you can say species E will go extinct. You could add, if it can't switch food sources. You would typically imagine in a food web like this, that if B was a possible food source or C was a possible food source for E, then you would have an arrow there. And if this was a weighted food network, food web, then you might have, say, 90% of its food is coming from A and 10% from B. And then if A goes extinct, it switches more of it to B. But here we don't have that information. So all we can say is that species E will go extinct. Question, yeah. Yes, so I will add it in up here. Species F and D will lose a food source. Species D will go extinct because it loses its only food source. That's a reasonable assumption to make based on the information that we have. Like I said, there are lots of other mites. Yeah. So H and I don't lose a direct food source. So A is going extinct, but we don't know what's going to happen to D and E, right? So only species A is going extinct. Oh, yes. No, sorry. That is a good point. Thank you. Sorry, I was thinking of you're a step ahead of me thinking of the knock-on effect. So yeah, that would also be reasonable to say. You could say when species E goes extinct, H and I lose a food source. So we often see these kind of cascading effects through food webs. When you start taking one part out of there or introduce something new, there are lots of knock-on effects. Again, there are lots of things we could then say might happen. If H and I lose a food source, maybe they switch more to D and F. But it's really difficult to intuit these complex feedbacks. Okay, part D. Find all the directed paths with initial point of one producer and terminal point J. I'm going to get rid of my scribblings here just to make this a little bit clearer. Okay, so we want to go from one of our primary producers and end up at J. Change the color here. Okay, so what are our possible paths? Okay, so we could start at, say, A, and then go to D, H, and J. So that's one path. We could go A to E, to H to J. So that's another path. We could start at B and go B, D, H, J, or we could go B, H, J. There are 4 different paths. There are no paths from C that lead to J. The 4 paths. How would I write these paths? I'd write them as things like A, D, H, J, A, E, H, J, B, D, H, J, and B, H, J. Okay, so you just write a path like that. Okay, hopefully these things are fairly straightforward. Okay, next thing. Compute the trophic level with respect to shortest path for all these species. And then in the second part of this, assume that only 10% of the energy at one level can be passed on to the next. Okay, so we start off at 100% of our energy at our primary producer level. Only 10% of this gets passed on to herbivores, and 10% of that gets passed on to the next level of predators, and so on. So the trophic level will tell us how much of that energy at the primary producer level is being passed on to the higher levels. And this is why you'll see far fewer predators than you will see herbivores, than you will see plants, okay? Because we have these inefficiencies. So assume only 10% of energy at one level can be passed on to the next, and we start off with 1,000 units of energy at species A, B, and C. At most, how much can be passed to species J and K? Okay, so first of all, work out trophic level with respect to shortest path. And then look at the second part. Just a reminder as well, the trophic level of our primary producers with respect to shortest path is 0. Okay, we're back to audience participation again. So, yes, that's what I like to see. Okay, just shout out what the trophic level is as I work through these. Okay, D.
1.
E.
1.
F.
1.
G.
2.
H.
1.
I heard some twos then. I.
2.
J.
2.
K.
3.
Remember, we're talking in this case for shortest path. So why is shortest path relevant here? Well, for the second part of the question, we're asking at most how much energy can be passed on. So if we were interested in what's the minimum, then we would be looking at, say, the longest path. Here we're interested in at most how much energy can be passed on. Okay, so the next part, we want to work out what is the maximum amount of energy that can reach species J and K. when we start off with 1,000 units at our primary producer level, okay? So we're going to have to take the product of 1,000 for each of these. So 1,000 units of energy and something else. Well, we're told that only 10% of the energy at one level can get passed on to the next. So let's think about species J. So species J has trophic level 2 here, and that's if we follow this path here. So starting at B, going to H, then going to J. So if we have 1,000 units of energy here, how many are we going to have at level H at most? 100, so 10% of 1,000. And then how much at J? 10, okay? So all we do here is we're taking 1,000 times by 10 to the minus 2. It's 10 units. Okay, what about if we're going to species K? Species K, suppose we are going this time from C through F through I through K. So here we do 10 to the minus whatever the trophic level is. Okay, in this case 3, it's going to be 1 unit. So you see that even though species J and K are both top predators, because J feeds on this omnivore here, so something that's feeding on a primary producer, it has the potential to get more energy from that primary producer level. Okay, show of hands who got that? Fantastic. Okay. We'll do another audience participation one here, why not? Now we're going to do the longest path. Okay, species D, E, F, G, H, I, J, A, D. Okay, a little bit harder now. This is where people start to usually get a little bit stuck, is the trophic status. So the trophic status, and it's telling us something a little bit different about the flow of energy through these food webs. We say that this trophic status for species X is going to be the sum of K times by NK, where K is the path length, and NK is the number of species that have path length K. So again, we start off with our primary producers having trophic status 0. What we can do is we can put this in table format. So imagine for species D, we're just going to list all the species that have a path to species D. And we want the longest path from that species to species D. Okay, so which species does D feed on altogether? A and D. Okay, so just 2 species. And what's the longest path of A to D? 1. Longest path of B to D. We add these things up. The trophic status of D is just 2. Okay, let's try this first. Species G. Again, we can just put it in a table. So you want anything that has a path into species G. So what has a path into species G? Well, D obviously does, because it goes straight into G. And then anything that D eats. So that's A and B. So D, A, and B. I find it's easier to work through the things that are closest and then work your way back. Okay. So the longest path here, species D has path length 1. Species A, longest path to G is, and B, 2. Okay. Trophic status of species G is just the sum of these things, so it's 5. Have a go at doing the other ones? There are quite a few of them here. So try and start off by doing J and K and then work your way back, because those are the harder ones. Okay, let's start with species J then. So species J, like I said, it's easiest if you work your way back from that species. So species H goes into species J and has longest path 1. Then we think about what does H feed on. So H feeds on D, B, and E. So let's just highlight those D, B, and E. Remember, we want the longest path from each of these to J. So the longest path from D, there's only one path, so length 2. The longest path from B, again, there's only one, so of length 2, and E also length 2. Oh no, sorry, ignore my B one. I'm being an idiot. Just made exactly the mistake that I shouldn't have made. D and E both have longest path length 2. What mistake did I make with B? I forgot that I took the shortest path, right? I forgot that there was also this arrow here coming out of B. So it has one path of length 2, but it also has this other path here of length 3. So the longest path from B to J is 3. What else do we have? We have, what do all of these species eat? So we have A, we also need to take into account. What is A's longest path? Well, it could either go this way, D, H, J, or it could go E, H, J, both at length 3. So trophic status of J is just going to be some of these things. So that's 3, 6, 7, 8, 9, 10, 11. We've got 11? Great. Okay, species K, I'll just quickly run through this one as well. Species K, well, I'm just going to highlight all of the things that feed into it. So it eats I eats E and F, E eats A, F eats A and B, and C. So I has path length 1, E has longest path 2, F has longest path 2, A, B, and C all have longest path 3. So trophic status of K is going to be the sum of these things, 9, 10, 11, 12, 13, 14. We got 14? Great. Okay, so I find the table format is the best way to do this. Okay, last one here. We've got exactly the same food web again, but now we've got weights on them. So I want you to calculate the weighted trophic level for each species, okay? So remember what these numbers mean. This 0.4 here and 0.6, say, feeding into I, means that 40% of I's diet comes from I and 60% comes from F. So we'll finish by computing these things. Another type of question to think about with this is, again, what happens if, say, F in this case is removed from the food web? I loses 60% of its diet. We could also think about if we know something about the total amount of energy that species I needs, or what is the population size to be supported by species E and F if there is a certain amount of energy at those levels, and it loses 60% of that, can it still survive? Okay. Or what happens to the population size? So you might receive a question like that. Okay, in this case, though, we're just going to compute the weighted trophic level. So remember the weighted trophic level, I'm going to call it TL here. The species I is going to be 1 plus the sum of the weights going from J into I of the trophic level of species J. Okay, so this is a recursive equation. You just need to look at what was feeding into it, into species I. That means you need to know the trophic levels of the things below. Okay. So in this case, we don't want to start from the top down. We definitely want to start from the bottom. And remember that our primary producers here are going to have weighted trophic level 1. Okay. The reason being they have 1 plus whatever feeds in, nothing feeds in. So it's just the trophic level of 1. Just to give one example here, if I do the trophic level of species D, it's going to be 1 plus what feeds into D? 50% of its diet comes from A and 50% from B. So it's 0.5 times by the trophic level of A, which was 1, plus 0.5 times by the trophic level of B, which was also 1. So as trophic level 2. Have a go at working those out for the other species. Okay, let's work through these together. Okay, so the trophic level of E, it's going to be 1 plus, it only has one thing it's eating, which is A. It's 1 plus 1 times 1. So this is going to be 2. Trophic level of F. F eats 3 things. We're going to have 1 plus, gets 0.2 or 20% of its diet from A. It gets 30% of its diet from B. And 50% of its diet from C. These all have trophic level 1 anyway. So this is going to work out to be 2. Trophic level of G. So here we've got 1 plus, it gets all of its food. So 100% of its food from D. D has trophic level 2. So G has trophic level 3. H now. H is a little bit more complicated. We have this 1 at the beginning, remember? So we have 1 plus, gets 10% of its diet from D, and D has trophic level 2. Gets 30% of its diet from B, and B has trophic level 1. Put these in brackets if it makes it easier. And then it gets 60% of its diet from E, and E has trophic level 2. So if I haven't made a mistake, this should work out to be 2.7. Okay, 3 more species and then you can go. So I, we have 1 plus 40% of its diet from E. E is trophic level 2. 60% of its diet from F, which has trophic level 2. This is going to have trophic level 3. J. Again, don't forget the 1 at the beginning. So we have 1 plus, it gets all of its diet. 100% from H. H is trophic level 2.7. So J is 3.7. And then last but not least, K. It gets 100% of its diet from I. I has trophic level 3. So K has weighted trophic level 4. Okay, here's the hint. Food webs are going to be on the final. Shocking. Have a good week, guys. I'll see you on Wednesday.